So today's class is about network diffusion. So we will talk about spreading processes on networks, and compared with last week where we were discussing about dynamic off networks, so when nodes and edges change a long time. This time we discuss about dynamic on networks, so where some properties of node are changing with time. So a typical example of spreading processes is, of course, viruses. So, well, of course, today everyone think about COVID-19, which you have read a lot about in media. But there are also a lot of other examples, like the Great Plague, for instance, which is also quite a well-known example. HIV, which is a virus that has different properties because it's much slower in time. So the dynamic of population, for instance, will play a more important role. Or other example like SARS, for instance, that have affected smaller or larger fraction of the world and of human populations. But of course, biological viruses are not the only processes we can study using spreading processes analysis or models of spreading on networks. One can cite, of course, malware spreading, like botnet infections or mobile malwares that spread not on human social interaction network, but more on technological networks, like the internet, for instance. An even more different example consists in studying social contagion, like information spreading. So when you have some either true or fake news that's happening somewhere is launched somewhere on the internet, this information can propagate among people and either reach a limited audience of a certain type of people or be widespread in the population if it's very successful. Another example would be rumor spreading. And adoption spreading. So, for instance, when some person starts to use a tool like Skype or I don't know, cell phones or Netflix or whatever, the fact that people use this tool can influence other people to adopt this tool or this software or this service. And people might adopt what their friends are using. And this way, this can also be modeled as a spreading phenomenon. And also political ideas like the Arab Spring, so-called Arab Spring phenomenon, in which several countries, some kind of uprising propagated from country to country. So why studying these processes of diffusion on networks? Well, because actually, as we have seen, many of these systems are organized into a network. And actually, when an information or a virus propagates, it's through interaction between nodes, between people. And so it's naturally by the network that this phenomenon of propagation occur. So the properties of the network will clearly have an influence on how quickly or how easily the process will happen. So one thing is that many elements of this course are based on this book. So if you're interested to go further, I encourage you to read it. And if you cannot find it, you can ask me. I can lend you a copy. The other thing is that currently, as you know, with the COVID situation, many people might there are debate on should we trust some information about the virus? Is it meaningful to do a lockdown or not? And many other questions. I just want to stress that I'm not an epidemiologist, and actually I have never published in this topic, so I'm not an expert. I'm just reading what has been written on the topic by other experts, and I just give you in this class a short introduction. So of course you have to trust the experts, epidemiologists who work on the topic, and after this class you will not be able to, I don't know, guide policies or really understand what's going on with the COVID. This is just an introduction to the topic, of course. So let's start with the most simple spreading processes in which we won't even actually diffuse on networks, but on a mixed population. So I will start by introducing generally the models from propagation, which are SI, C, and CIS models. And the general idea of these models is that each individual of the population can be in one of several states. So the first one, so identified by the letter S, corresponds to susceptible, and it corresponds to individuals being not infected. So you're not yet infected, you start as a susceptible. Then another state is infected. So of course, when you have been infected, but also you're contagious. You can infect other people if you have contact with them. And finally, there is a recovered or removed state. So in which you were infected, but you're not anymore. You either have totally recovered and cannot be infected again, you're immune to this process, or you consider removed. So removed can mean dead actually, or just you cannot be infected again and you cannot transmit to anyone else. So whatever happened to you, now you're not part of this spreading process anymore. So every individual must be in one of those states, and later we will identify as ST the fraction of individuals in the susceptible state at time t, by IT the fraction of individual in infected state, and so on. And also we define I0 as the initial fraction of infected individuals. So obviously, if no one is infected in the beginning, then there's no way that the propagation will occur. So you need to have some initially infected individuals. So this is a general drawing of the different models. So in the first one, you see that you can go only from susceptible to infected, and the probability to go from one to the other will be a parameter beta that I will detail later. In the CIS model, you can go from susceptible to infected, but then you can recover. So you can go from infected to susceptible with also a different probability. And finally, in the CIR model, you can go from susceptible to infected, and then from infected to recover. And you cannot go backward in this process. So as I said, in the first setting, we do not have a network, we just have a population, and we consider that anyone in this population can interact with any other person. The population also has a finite size, and individuals have an average number of contacts per unit of time. So everyone can interact with any other person, but they don't do it every step. So we need 3 parameters. The first one is called the infectivity. It's the probability that a contact between an infected and a susceptible individual results in the infection of the susceptible. Okay, so if two persons interact, one is infected and the other is not, what is the probability that this second person become infected? So the contact rate is what I described just in the slide before. It's the average number of contacts per person per time. So with how many random other individuals do you interact at every step, let's say, of the process? And finally, we can also define beta as the effective contact rate. And so the effective contact rate is just a multiplication of the 2 previous one. So it's actually represents the number of newly infected individuals by each infected individual in a population in which everyone else is susceptible. Okay, so if you have a beta of 3, it means that at each step you will infect infect 3 different other individuals at the beginning of the process when everyone else around you can be infected. So in the SI model, what you will have is something like this. You start with someone who is infected, and it can infect other people in the population, and you will have, in this case, more and more infected individuals in the population, and it cannot stop. So let's look at the characteristic of the SI model we have just defined. So we have said that in average, each infected individual infects B other individuals. But this is true only if everyone else is susceptible, which is not the case a long time, because a higher and higher fraction are already infected. So to compute the rate of new infection a long time, so how many new people become infected at every step, we need to multiply this beta by S, the fraction of people who are actually susceptible. And we multiply this by I because there are already I fraction of the people who are infected, and thus so the more I is high, and the more people can become infected because they are in contact with more infected individuals. So we can remark that since S equals 1 minus I, then the derivative of I along time is actually depends only on beta and I. And this is the first observation that we can make, is that if when we are at the beginning of the propagation, when we have only very few people who are infected, I is close to 0, so this is close to 1, and so we can describe the derivative of I along time as beta I, and this actually corresponds to an exponential growth. So this tells us that at the beginning we will have an exponential outbreak, so it will grow exponentially fast. So this is again a term that you have probably heard in the news, and this is explained by these simple equations when we are at the beginning of an outbreak. The second observation that we can make is that obviously there is a saturation when nearly everyone is infected. Then the growth is much smaller for the last person of being infected, because most of the people you actually interact with are already infected. And another observation that we can make is that the growth is actually faster and faster until half the population is infected. So this means that we have a very fast growing rate of infected people in the beginning. So I also give here the analytical solution of the infected fraction of individuals along time. I don't do the derivation as usual. You can find it in this book that I already cited before. And this will be true for most of the analytical solution I will present in this class. Another observation we can make is that as long as beta is above 0, so if there is at least a probability to infect someone else, then everyone will be infected in the population at the end. It can be, of course, slower or faster. The rate is not always the same, but in the end, everyone gets infected. So you might wonder how realistic is this. So hopefully for us, this is not what's happening with biological virus like COVID. But it can be, for instance, used to model what is going on with technology adoption. So when a new piece of hardware or service appears, like for instance, the radio or the electricity, or I don't know, the TV, the color TV, and so on and so forth. You can model it with this kind of process because so when someone buys a TV, then the neighbors, if they don't have a TV, they want to have one, and the more neighbors they have who already own a TV, and the more they want a TV. And so you will have this exponential outbreak in the beginning. And in the end, well, there are always a few people who are reluctant to buy the TV, and thus you will have this typical S curve. So you can clearly see that in reality it's not the case for all the phenomenons, but nevertheless you clearly see that there is often this exponential start of the diffusion. So let's start the second model, which is the SIS model, in which now people can recover. So this is a good news. So we have to introduce a new parameter, this mu here, and it's called the recovery rate, and it tells you at which rate do people recover. So hopefully, if people recover faster than they can become infected, then the propagation will stop. So what are the characteristics of the SIS model? So the SIS model is actually quite similar to the SI model. And the difference will be that when I describe the rate of new infection here, you have this part of the formula, which is exactly the same as before. But you also add this part of the formula, which describes the fraction of individuals which that switch from infected to susceptible. So switch back from infected to susceptible. So from this new equation, you can obtain also the infected fraction, and which is described by this formula. And what is interesting with the infected fraction is that if we observe what's going on when t is growing towards infinity, we can observe that this fraction actually tends towards 1, because this becomes very small compared to the rest. So when t is large, this equals 1. And thus the formula is completely described by this part. And this tells you therefore that the fraction of infected individuals can be described in only using these two parameters of the model. So this is what I have described in this figure, and you can see that so exactly like SI, you start by an exponential outbreak, but this time instead of stabilizing at 1, so reaching the stage in which all the population is infected, this time we know that we will reach a threshold which is equals to 1 minus mu divided by beta. And and we will stabilize at this point. So why? Because you have always the exact same number of people going from infected to susceptible than people switching from susceptible to infected. Okay. So on this model, we can introduce a new ID, which is the delta ratio that, again, you have probably heard in the news as the R0 or R0, which is an important notion which tells you if there will be an outbreak or not. So will a significant, if you start with only very few infected nodes and very few infected individuals, will you see that an outbreak will start? So you will have a significant fraction of the individuals infected or not. And so this value can be computed again only from the parameters as the fraction of beta over mu. So it can be understood as the average number of individuals that will be infected by an infected individual in a population in which all other nodes are susceptible. So this tells you nothing about how the virus or the process will evolve after a long number of t, but it tells you if in the beginning the propagation will start. And the important point is that there is a threshold at a value of 1. And if R0 is above 1, then there will be an outbreak. And if it's below 1, then the epidemic will disappear naturally. So this can be understood very easily. It's that on the right, you have this figure that will represent a delta and R0 of 2. And this tells you that one person, during the time that this person is infected, it will infect 2 other people. And each of these 2 other people will infect also 2 other people. Because in the beginning, it won't decrease because we consider that everyone else is susceptible. So you can infect the maximum number of individuals that is possible, which is beta. And so obviously you see that this corresponds to an exponential outbreak, and that's going on if your R0 is above 1. If your R0 is below 1, then it means that in average, during the time that you are infected, so during the time that you can infect other people, you will infect less than 1 person. So obviously, if you start with 5 people infected, then when they are not infected, they will have infected only maybe 4, and then 3, 2, 1, and the virus will stop naturally. So when you hear in the news about this R0 that we try to keep it or to make it go below 1 by maybe asking people to wear masks or to installing lockdown, that's what policies are trying to achieve. It's to really stop this propagating, this exponential propagation process, and to therefore has the process disappear naturally. So let's move to the last of the 3 models I want to present in details, which is the SIR model. So again, similar principle, but this time when we are infected, we cannot go back to the susceptible state. Instead, we can move to a new state, which is recovered. So as I already said, recovered can means actually removed. So you are either dead or not able to be infected again. And this is more what could correspond, for instance, to the situation of the COVID, while the previous one corresponded more to something like the flu or the influenza, so something which is coming back every year. And people can get it during 1 year and then they recover, but the following year or even later the same year, they can get infected again. So for the COVID, as of today, we think that in most cases you cannot get reinfected. So we have this situation that if you're susceptible, then you can become infected, and when you're infected, after some times you recover. And when you recover, you cannot be infected again, and you cannot infect other people. And so we use this parameter to model this probability of transition from infected to recover. So it means that it's actually a recovery rate. So it tells you what is every time step, what is the probability that you recover. So let's look at the characteristic of this SIR model. So we see that we can model it as a set of differential equations, just as before, but I won't go into details about it. You can look at it in details in the cheat sheets if you want. However, what we observe, what's interesting to observe is the typical scenario of an SIR propagation. This time you see that, as before, we will start with the fraction of infected individuals having an exponential outbreak. So it will start as an exponential, but unlike before, you will reach a peak and then decrease, obviously, because the fraction of recovered individual also grows, and when people are recovered, they cannot become infected again. So you will have the number of infected that naturally decrease until reaching zero. Well, all the possible individuals to infect will be infected. But what you can observe, which is interesting, is that the fraction of recovered and thus the fraction of susceptible are not reaching 1 and 0, which means that some individuals were never infected. So in this SIR model, you can have people who naturally never get infected, even though the propagation process is ended and the virus stops its propagation, disappear. Other observation to make is that the delta ratio that we have defined before, again, still exists. This time it's defined as beta over gamma, but it's exactly the same idea as before. And yeah, I think that's all. We have, yeah, the important thing is we still have this exponential outbreak. So there are also different models that have been proposed in the literature, like you have some of them here. Sometimes with different ideas, like instead of having a fixed beta, which is always the same, so every node has the same probability to infect other individual, you can imagine more complex scenario, for instance, in which the number of individuals you will be in contact will affect your probability of becoming infected. Like, for instance, the majority rule will be that if you have only less than the majority of your friends that has a particular opinion, for instance, a political opinion, then you won't have the same ID as them. But as soon as more than 50% of your friends have a particular ID, then you're very likely to also agree with this ID. So this will be a scenario that we can define on more on networks. So if you want to check some of these models, you can go to this link, for instance, where some of them are listed with references to their description. So let's now start the core of the topic, which is spreading on networks. Because I remind you that until now, we have described those spreading processes on population in which everyone can interact with everyone. But what's going on when we have a spreading situation on a network? So clearly, the homogeneous mixing approach we have seen until now is unrealistic. So interaction occur on networks, and this is probably important. So for instance, if you start with this node infected, then you will, at the next step, maybe switch to this situation. Then this node can infect this one and this one. But for instance, if this node recover, switch to the recovered state, then this part of the network will never be infected, because they can be infected only by this person. And if this person is cured before infecting this part of the network, then this part of the network will remain healthy. So we see that the network can be important. So how much does the structure of the network affect the spreading? So just a detail of formalism, but here the C we had described before, corresponding to the average number of interactions per unit of time, is not necessary anymore, because this will be actually represented by the network itself. So each node has a given number of neighbors, and so this number of neighbors will define how many interactions I have. So this node, every time step, will interact with these 3 nodes, and this one will interact only with this node. So for this reason, we keep beta as a parameter, but beta is now equals to what was before tau. So this beta corresponds to the probability of transmission when two nodes are connected together. So if this node is infected and this one is not infected, then every time step of the simulation, it has a probability beta of infecting the other node, each of the neighbors actually. So the question I asked was if the topology, the structure of the network will affect the propagation. And obviously, we can find example where it is the case. So for instance, if we take this lattice network and we imagine that we have a node infected in the beginning, I don't know, maybe on this side, then you see that clearly the propagation will be relatively slowed down by the process, because you will need to have infection by infection to progress in the graph until reaching the other side. Also, you see clearly that if this is a single graph in yellow here, if this graph is disconnected, so you have several connected components, then obviously you cannot propagate from one side to the other. So if this part of the graph on the bottom get infected, then if this not get infected, it can infect all the two others, but the rest of the graph will remain safe. And that's actually what policies are trying to use for the COVID. It's to try to isolate some part of the network as much as possible to avoid propagation. And obviously, there are also examples in which, so if you imagine a network in which everyone is connected to everyone, or a network in which you have one node in the center, obviously these correspond to different also scenario of propagation. But in general, if you have a complex network, what is the effect of its structure on the propagation? In the first case, we can consider homogeneous networks. So an homogeneous network is defined as a network in which all the nodes have exactly the same degree, in this case. So if they have exactly the same degree, even if it's a random network, then we can observe that actually the process is really equivalent to having an homogeneous mixing on the general population without a network structure. So the way to model this the propagation on the homogeneous network is through this equation. And if we compare it with the original equation on the homogeneous mixing, we see that it's very similar, right? This one and this one. The difference is that here I have introduced the degree, but if you remember, I said that this beta is actually the probability to transmit the infection to each of the contact I have multiplied by the average number of interaction I have at every time step. While here it's actually the same thing, because this K will really correspond to the C hat I had before. So in practice, there can be a few differences, such as the switch from continuous to a discrete setting, but it will be very, very similar. It can be considered similar in the general case. On a more conventional Erdős-Rényi random graph, in which we have seen that the degree distribution is Poissonian for large graphs, then the approximation still holds, because we have seen that the average, the distribution of degree is actually very narrowly centered on the average degree. So we can consider that the degree of each node is approximately the average degree. So we get back to the situation of an homogeneous network, and everything goes as in the homogeneous mixing situation. So if you have a completely random network, it doesn't make a difference with homogeneous mixing. So it was a good approximation. But the problem, of course, is that we have seen in previous classes that real networks, they often do not have an Erdős-Rényi random graph structure. They have heterogeneities, and these heterogeneities can correspond to different, wide heterogeneity in degrees, or some topology like community structure, or some spatial structure on which we will discuss in the next class. So the most common heterogeneity on network is the heterogeneity in degrees. So when we have, for instance, a power law degree distribution. So in this case, we know that the degrees of nodes will be very different, and thus our approximation of for which the degree of each node was approximately equal to the average degree cannot be used anymore. So the solution to this problem is to use a degree block, what's called the degree block approximation, in which we will consider that all nodes having the same degree can be considered as a single homogeneous group. So for instance, you will put all nodes with degree 1 in one group, all nodes with degree 2 in another group, degree 3 in a group, and so on and so forth. And you will handle each of these blocks independently to obtain, to be able to study analytically what's going on in such a network. So we define a new new values like I little k, which correspond to the fraction of infected nodes among all nodes of degree k, and sk corresponds to the fraction of susceptible nodes in all nodes of degree k. And having these values for all the k, so all the nodes of degree k, we can compute a global average and finally obtain the total fraction of infected nodes by computing this sum over all the possible degrees of the fraction of nodes having a degree k multiplied by the fraction of infected nodes among them, and same thing for susceptible. So let's look at what's going on with the most simple model, the SI model for this when we have a heterogeneity of degrees. So first, just as with the homogeneous network, we still have everyone infected in the end. So this does not change, but what can change is actually the speed of the process. So how fast are you infecting all the nodes? And to solve this problem analytically, what we start by doing is by defining this differential equation of the fraction of nodes of a given degree that gets infected a long time. So if we compare this to the equation for the homogeneous network, we observe that it's pretty similar, but we are focusing on a particular degree. So what are the differences? Well, we can use directly k instead of the average degree here. This part of the formula that represent the fraction of the node of degree k that are not yet infected. So now it's among nodes of degree k instead of all nodes. And finally, the most important change is this I, which was representing before the fraction of all the nodes that were infected, so that could infect the current node. But in this case, this depends. We consider that this can depend on its degree. So the nodes with a given degree do not have the same fraction of infected neighbors. Okay, so this represents the fraction of infected neighbors of a node with degree k. So there are two phenomena that explain why the approximation does not hold. The first one is the friendship paradox. We have seen this in previous classes, that the average degree of neighbors of a random node is actually higher than the average degree in the network overall. So this explains why this heterogeneity of degrees will impact the probability of being infected. And secondly, we have also seen in other classes the problem of associativity, and that in many real graphs, there is some specific degree-degree correlation. So for instance, a rich club in which high-degree nodes are more likely to be connected to other high-degree nodes. But in this approximation, we will just ignore the second part. We will consider that we will consider the case in which there is no degree-degree correlation. And so we just have to be careful of the friendship paradox. So this means that this probability of this fraction of infected node in the neighborhoods can be in the general case be computed like this. So it's the sum for all the possible other degrees. What is the probability to be connected for a node of degree k? So we are computing for all nodes of degree k. So we are observing what is the probability of this node of degree k to be connected with a node of degree k prime. And what is the fraction of nodes of degree k prime that are infected? So this way we can compute the fraction of nodes that are infected in the neighborhood of a degree block of degree k. So by computing this without degree-degree correlation, we see that the probability to be connected with nodes of degree k prime for a node of degree k can actually be simplified by this formula. And you see that here there is no mention of k. So this actually does not depend on the degree, just depends on the distribution of degrees, right? So p k prime is a distribution of degree. And yeah. From this, we know that the theta k is actually the same for all k. So we can just compute the average fraction of neighbors that are infected in this way, which is just so computing for all the other degrees. What is their degree multiplied by the fraction of nodes which have this degree, and the fraction of them that are infected. Okay, so in the end, it does not depend on your degree. What is the fraction of your neighbors that are connected? And this becomes interesting when we study something which is called the time scale. So again, I'm skipping the details that you can find in references, but the time scale is a notion that measure which is inversely proportional to the speed of the diffusion. And from the previous equation, it can be shown that the time scale of a spreading process on when there is a heterogeneity of degrees can be expressed in this way. And as you can see, this depends on the average degree and on the variance of degrees. And this tells you that the higher the variance, the more the time scale will be small, and thus the diffusion will be fast. So for a given average degree, so if we fix the average degree and a given beta, of course, the higher the heterogeneity, the faster the diffusion. And actually, if you remember what we have seen on the class on power law degree distributions, you remember that if the exponent of the power law is below 3, then the variance diverge towards infinity. So it tells us that this becomes actually very close to 0. So the time scale becomes nearly 0, tends towards 0, which means that in theory, the diffusion is nearly instantaneous. And you can actually understand this by imagining, if you imagine a graph like this one, in which you have such a heterogeneity of degrees that there is a node which is connected to everyone. So what's going on in this case is that if any of the other nodes is infected in the beginning, then it's very likely that the central node will well, it can potentially become infected. And so if depending on the beta, it will actually become infected after a few steps. And when this node is infected, then it's over, because since he's connected to all the others, the spreading will, the infection will spread very, very quickly. So that's the general idea. So if you have a higher degree heterogeneity, then the diffusion is faster. So this can be checked experimentally. So if we increase the variance of degrees, we see that with 3.1, it's this curve. 3.5, you get this curve, and so on and so forth, until when you have a very high heterogeneity, you have something which is nearly instantaneous. The fraction of infected, so everyone becomes infected very, very quickly. So a second case we can look at is the SIS process, for the SIS process, but it's also true for the SIR one. And it's when we look at this lambda, or the R0 that we have already defined, in which we have seen that if this ratio between beta and mu is above 1, then there will be an outbreak. So the virus or the infection will spread at least a little bit in the network. And so in the case of networks, it's written a little bit differently, because we have this average degree instead of the C in the beta. So you can write it this way, but it's exactly the same idea, that if this ratio is above 1, then you have this outbreak. So this is for homogeneous network. But if the network is heterogeneous, then it can be shown that, you have an outbreak if lambda is above the degree divided by the variance of the degree, and not 1. So this means that even if you keep the same beta and the same mu, but you apply it on a network with a high variance in degrees, then even if this ratio was before below 1, but you have a high variance, then you can have an outbreak. So yeah, so this means that in a very heterogeneous network, an outbreak can start even if lambda is very small and below 1. And this can have strong implications, because as we have discussed before, this R0 is something you hear about a lot in the news. And we usually compute, so this R0 is computed based on data. And the objective, for instance, for the COVID, is to make it go below 1 with using lockdowns and masks and so on. And the problem is that if actually we are considering that the social network on which this virus propagates has a heterogeneous degree distribution, then even if it's below 1, it doesn't mean that necessarily the outbreak will, the diffusion of the virus will stop. So until now, we have studied the influence of the network structure theoretically. But in this last part, I will show some experiments that in practice, what is the effect of some element of the structure. So one thing we can look at is at the community structure. So we have described that you have a community structure in a network when we have some groups which are strongly connected inside the group and more weakly connected to the rest of the graph. And we have seen that this is true for many networks. And also, if you think about, for instance, the network of interaction between individuals in society, clearly you have this community structure. So what is the influence of having such a structure? So what I do is that I fix a number of parameters. So I fix the number of nodes, the average degree, and then I compare an Erdős-Rényi network with some networks with community structure. And to vary, so I fix the number of blocks at 100. So I have 100 communities, so communities of size 10. And I vary the fraction of all the edges that are inside the communities. So at which point are the communities well defined, or is it closer to a random network? What we observe is that in the beginning, so if you look at small values, so when we are close to a random network, we see that obviously the Erdős-Rényi and the weakly defined community structure are similar. They show similar behaviors. But when you start to increase the fraction of edges inside community, so you have these communities which are much more clearly defined, then you observe that the fraction of infected node and the speed at which these infected nodes, the fraction of infected nodes increase, is becoming slower. And finally, when you have actually communities which are very strongly connected together, but with very few edges to other communities, you observe that the spread, there is not even a real outbreak. So the infection just disappears by itself, even though the graph is still connected at this point. So this was checked for being connected. So we see that the community structure has an effect, which is to, if you have a strong community structure, then it will make the diffusion harder in the network, which is rather good news since we have seen that in many networks you have some community structure. But the bad news, I don't go into details here, is that where the outbreak started, all the nodes in the same community have higher chances to be infected, while nodes in other communities are less likely to be infected. So that can explain also some elements about what's going on with the COVID. Is that when a country starts to be infected, then usually you have a high outbreak in this country, but some other ones can stay unaffected. But it's a little bit, well, sometimes it can also be by chance. It's not necessarily that they have offered the best solution for their citizens. It can just be that because they are relatively poorly connected to other countries, then they are less likely to be infected by other countries and thus stay out of the infection. So the second experiment is with scale-free networks. So what I have described before, in which I generated, so again, an Erdős-Rényi network, and then skipping the same number of nodes, skipping the same average degree, I just modify the degree distribution using an exponent, which is going from 2 to 4. And here what you observe is that if you have a large exponent, which means that the network, the degrees are not that heterogeneous, then the situation is relatively similar to an Erdős-Rényi random graphs. But as predicted by theory, when the exponent becomes large and you have a typical scale-free network, then the diffusion is much faster than what was expected on an Erdős-Rényi random graph. So this is bad news because it says that for real graphs, for diffusion on real graphs, it will be worse than expected on the homogeneous mixing theory by the theory of homogeneous mixing. And then the last case is exploring what's going on if you have some what I call a spatial structure. So I will go into more details on spatial networks on the next class. But just today, let's take an approximation with a Watts-Strogatz random graph. So if you remember, in a Watts-Strogatz graph, if you don't add randomization, you have something like this. You have a circle and nodes are connected to their neighbors. So they have a high clustering coefficient, but there are no shortcuts. So this can be thought as a spatial structure in which nodes are more likely to be connected to nodes that are close to them in space. And they are less likely to interact with nodes which are far away in the network. And So what we study here is when we add shortcuts, how does it affect the spreading compared with the Watt-Strogatz without shortcuts? And so if we don't have, so the Erdős-Rényi case is this one. And if we consider that we have no shortcuts at all, then we can observe that with the same parameters, the outbreak, the infection tends to disappear naturally. The idea is that since you have to go through a chain of infection, if your probability of infecting your neighbors is not that big, then at some points in the chain you might stop just by chance, and then you stop your propagation, and the other nodes which are on the other side of the network are safe. When you add some random nodes, you see that quite quickly the speed of the infection and the fraction of edges which get infected increase. And yeah, so when you have a graph which becomes closer to a random graph than to an Erdős-Rényi random graph, then the diffusion becomes similar. So to finish, I wanted to discuss about applications of what we have seen on real situations. So the first thing we can do is model fitting. So if we have some network that model a population, and we have observed data of which node got infected first, then we can fit the parameters of our model, so the beta, the gamma, and so on, to try to explain as closely as possible the observation by a model. When we have done that, another thing we can do is to predict future trends by just running the simulation of the propagation on the network with the parameters we have learned. And finally, what we can also do is to prospect what is the most efficient way to fight, for instance, an infection by using some control. So, for instance, let's imagine that you can remove nodes, maybe by giving them a vaccine. Or you can remove edge by, for instance, by making it impossible for some people to interact. Then, which node or edge should you choose to fight to limit as much as possible the propagation of the virus? So you can try to do that experimentally, or you can try strategies like removing nodes with the higher degree of, or maybe with the higher betweenness centrality, because this will tend to create communities. Or yeah, so you can test these kind of strategies. Another interesting idea, I think, is using the friendship paradox. So this was proposed by some authors in the literature. Let's imagine that you have the situation of a movie like Pandemia, in which a virus has been designed, has been created by scientists. But of course, they cannot vaccinate everyone in the world population immediately. So they have to make some choices to whom they should give the virus, the vaccine, the cure first. And to try to be fair, what they do is to distribute it randomly. But randomly to people. But this is actually not the most efficient strategy, and the authors propose to use the friendship paradox to do it still randomly, but with more efficiency. So the idea is to pick random individuals, and then to ask them to give or to check who are their contacts. And by picking at random contacts of individual nodes, we are in average picking high degree nodes. So instead of giving the cure to random nodes, you give the cure to random neighbors of random nodes, and this way you should be more efficient while still being random. So of course there is no guarantee that this will work in practice. So I wanted to finish this class with an example of a recent article that was published actually last week, which corresponds to, so it's called Mobility Network Model of COVID-19 Explain Inequalities and Inform Reopening. And it has been written by authors which are network scientists, computer scientists, and some people from as you can see, in preventive medicine and policy research. So even though it's not really a paper by epidemiologists, I think it's close enough to a real model that could be used to fight the COVID pandemic. And so the idea of the paper is that they use data coming from a company called SafeGraph that aggregates anonymized location from mobile applications. So this company was collecting this data even before the pandemic. And so they, in the paper, they use data from March to the beginning of May 2020, and they have data about hourly movements. And in more details, what kind of data do they have? So they have information of trips between census block groups and point of interest. So this census block group, they correspond to small area of 600 to 3,000 people. So it's a little bit like the Iris in France. So they so it's just some correspond to some areas with small populations, and so it's anonymous, so they don't know who is exactly the person who moved from this neighborhood, but they know that someone from this neighborhood has moved to a point of interest. And point of interest are things like restaurant, grocery store, religious establishment, and many others. So I think they have about 15 categories. So they know the category, and they know the exact location, so X and Y of both the census block groups and the point of interest. So they really have, so they have, with this data, they have a network. It's not a network in which nodes correspond to individuals, but it's a network in which nodes correspond to areas or point of interest. So it's large-scale data because they have 98 million people, well, trips by 98 million people. They have 60,000 area about approximately, and more than 500,000 point of interest, and more than 5 billion edges over the period. They have this for several metropolitan areas like Chicago, New York, but they fit a separate model on each of these metropolitan areas. There is no connection between them in the model. So so they have a different model for each city. So they used a model which is slightly different than the one I have introduced until now, which is called SEIR. And the difference is that there is another state which is called exposed. This is because for the COVID case, people often get infected but do not become sick immediately. For sometimes they are called exposed, which means that they will become infectious, they will become infected and infectious, but not immediately. They stay in this stage for some time. So that's why we have, so this needs to be taken into account for the model to be realistic. So so from exposed to infectious, which is the only difference with the SEIR model, the disease progress in the affected person, and you have a probability to go from exposed to infectious. So I won't go into too much details, but just to give you an idea, these are equations that decide of the fraction of nodes which are exposed that will move to infected, or the fraction of infected that will move to recovered. And we see that these two equations are parameterized by these that correspond to the mean latency period and the mean infectious period, and which are known from studies in the literature about this particular virus. Okay, so these are not learned, they are known from medical studies. And the probability to go from susceptible to exposed, so to get actually kind of infected, because that's when you move to E, you will become infectious a little bit later. And so this equation is a little bit more complex, but so we will detail it in the next slide. The idea is that it will depend on the rate of infection at each point of interest and of the visit matrix from the mobility network. So it depends on the network and on what's happening at each of the point of interest. So for a particular point of interest, the infection rate at T depends on the fraction of infected visitors and on the transmission rate beta. So it depends on who is visiting and on this transmission rate. And the transmission rate itself, it depends on factors which actually are really specific to this point of interest. So in particular, it depends on the size, the area of the point of interest, the number of visitors at T, and a learned parameter. So the idea is that the more crowded is the point of interest, the more likely it is to get infected. And these parameters is something that we learn to know from a given number of visitors and a given size. So for a given crowdedness, how much does this affect transmission rate? So basically, that's the parameters this is the parameters that need to be learned. So to sum up on the model, the idea is that we have this network, which is known for every 1 hour, for every period of 1 hour. We have the network between the census block and the point of interest. Okay, so it can be different from 1 hour to the next. And we know from where people are coming and where they are going. And on the other side, we also have a model which is trained for each of the area. So the parameters of the model are the same, but the fraction of susceptible and exposed and infected and infectious and recovered are different for each of the areas. And that's the point, actually. Well, one of the points is that we can consider that some part of the city can be already quite be quite well infected, while another part of the city maybe is not as much infected. And this is exactly what we want to take into account. To sum up also, they have only 3 parameters to learn, and these parameters are constant over time. So it does not change. You have just to find the proper value once and for all. The first one is the scaling for the point of interest. So what I already explained, it depends on the floor area of the point of interest, which is basically a proxy for the beta parameter in point of interest. They also learn the transmission rate beta in the areas, in the living areas, and the initial proportion of exposed individuals. So they fit these parameters using the root mean squared error. So basically the idea is just that they try different values of these parameters, they run simulations, and they check what are the parameters that will give results as likely as similar as possible as what has been actually observed. And that's it. So that's what they have done. They fit these parameters, they run the simulations, and then they check. So the first thing they can do, as I mentioned before, is to predict future trends. So here, for instance, they calibrate the model on 2/2 of the data, and they try to predict the last part of the data. And so you can say that it fits or it doesn't fit. Well, it depends on your what is what are your expectations. But we consider that the results are good enough. So in this case, they do the same thing, but they fit on all the data. So they cannot predict. Well, they could use this to predict the future, but it's more to really check if it's evaluate if the method is efficient. It's better to use this kind of method in which you can check on your prediction if the results are good or not. Then they can do what I call what if scenarios. So in which they will test with this model what is going on if they change the mobility, for instance. So let's say that in average, so this is what happened. There is no, so sorry, this is what happened with some lockdowns. And they compute what would have happened without the lockdown. So if there is no reduction at all, we can see that the number of infection is obviously much larger. And if they reduce only to 50% of normal, you have this reduction. They also test what's happening with the timing of the mobility reduction. So if you do the lockdown later or earlier, what is the effect? So you probably also have seen this kind of plots in the news, in which you can just play your model and see what is the result. And obviously, if you start the lockdown earlier, well, you will reduce the fraction of infected individuals. Here they explore the what is happening if you reopen partially the point of interest, and here they predict the increase in infection from reopening different point of interest. So, for instance, if you reopen the restaurant, you will get a number of additional infection which is very large. While maybe if you reopen car dealers or convenience store, you won't add so much new infections, which can be because less people are going to these places, or because these places are maybe less susceptible to be the cause of infection. And then what is also very interesting, I think, is to use their observations and model to explain some social phenomenon. So, for instance, it's known that the COVID has been had a worst effect on poor people, so the bottom income of the population, compared with top income population. And so, they study some factors that could explain this. So, for instance, they observe the per capita mobility between these two deciles. And we can observe that the bottom income decile had a mobility which is actually larger than the top income decile after the lockdown. So it was lower before the lockdown, and it's higher after the lockdown. So why? It's probably because there are more essential workers, like people working in grocery stores, or people people working in hospital, also, or people, so that have to go to work anyway, lockdown or not, that cannot do distance working. So that might be one explanation. So this comes from the data. Another thing they study, this time based on the model, is what is the transmission rate by category of point of interest. And on the x-axis, you have for the average transmission rate for top income, and the average transmission rate for bottom income on the y-axis. And so you see that for some types of point of interest, it's the same. So for general stores, gas stations, and so on, it's not that much that important. But for religious organization and for hardware and grocery stores, for instance, you see a big difference. So this means, so it's transmission rates. And so this says that if someone from the bottom income goes to one of those places, this person is more likely to get infected if it's from the bottom income decile than from the top income decile. And why? Well, they also check in the data that this is due to mainly to initially smaller and more crowded local stores or local religious places. So since it's more crowded in the beginning because it's smaller in particular, so and more people are going to these local places, then they are more likely to get infected. So then people going to these places are also more likely to be infected. Well, to be able to spread the virus. And so this leads to a higher probability to get infected for people from the bottom income population, even if they have the same behavior. And finally, this kind of studies can also be used to maybe guide some policies. So in this case, they look at the predicted infections by category. So by depending if you're a bottom income or top income decile, what is the most likely cause of being infected? And we see that there are very different patterns. So for instance, for the bottom income decile, it's more likely to be infected from restaurants, religious organization, and grocery stores. While for top income deciles, you see clear peaks for cafe and snack bars and fitness centers. So that might be, So you see these differences. And maybe this could be used to take some decision on how to fight the situation. So obviously, you have to be very careful with this kind of interpretations. This is just a model. I'm not saying that I trust this model. I don't actually know, but because I'm not an epidemiologist, and I think it's a complex problem, but it shows how this kind of model can be used to at least get insights of what's going on and propose solutions or give insights.